Welcome, everybody. Thank you for traveling across wherever you came from, and even if it's just from up the road, and getting up very early in the morning, jet lag, to come down to this talk. Hopefully, we'll find something interesting that we can tell you. I'm Charles Clark. We have Fernando Diaz from Google, who is out there in the ether somewhere, who will come in shortly. And then we have Nagar Arabzadeh, am I getting that right? Who is my student at Waterloo. And we do this preference-based offline evaluation tutorial. And the reason we do this is that search engines and recommendation systems and so forth have gotten now almost too good. Okay, so the traditional ways of doing offline evaluation, well, having tried to do them in industry, they actually are very difficult to get right, and we'll come back to that. But also that now if we have neural rankers, everything surfaced by a neural ranker is highly relevant, perfect. You know, if you do point-wise evaluation, if you ask a person, is this a good answer for this query? They're going to say, yes, that's fantastic. That's really, really good. And in fact, people, Nagar and I did some work with some other people where basically, if you look at things from a preference standpoint, in fact, the things that are known best answers, sometimes the things surfaced by the search engines now are better than the best known answers. And also for evaluation exercises like track and things like that, they're basically, well, everything we have now is highly relevant. So how are we going to measure the systems? A long time ago, I worked for a company building search metrics, and the company might have had a product that looked like this, okay? And I like this example because the query was Trump. That's a guy that used to run the United States sometime in the past, if you remember. And here are 2 pages associated with this gentleman that I hope we'll never see again, but you never know. This is the page for him as president, and this is his private page that I think can come back these days. And the question is, this really was one of many examples that inspired me at that time. If you evaluate this in isolation, both of these are absolutely perfect responses to the query Trump. There's no, if you're used to writing relevance guidelines for search, there are no guidelines you can write that would ever possibly say that these aren't perfect results. But if you look at other clues that are available, here are strangely, some of my friends follow him. There are at that time, 24 million people that followed him. Here are only 2.7 million, so almost 10 times as many people. So if I put these side by side and I say, what should be the response to the query Trump? The answer comes out here. But the only way you can possibly know that is by making a comparison and by applying rules that can only be applied if you make a comparison. So I left that company. We were doing stuff, went back to audit, and I said, I have to figure out how to make preference judgments work in a broad way. And as you'll see, they're going to work preference labels, not just preference judgments, but preference labels saying this result is better than that result, does a bunch of things. It's a much more simple judgment if you're having humans do it. You can infer preferences from online interactions. And these days, you can even ask large language models, which is a better thing. And that's an easier, well, we won't get too much to that, but that's an easier thing than asking, is this relevant or something like that? Okay, so that's my introduction that's my motivation. What we want to start with is we want to step back a little bit and look at first preferences between rankings, which is Fernando is going to take care of that part. And then just the schedule for this morning is that Fernando's going to talk about this. I'm going to talk about preferences between items. Nagar is going to do a demo of some of the tools that we built in this area. And anytime, don't hesitate to ask questions, because in this kind of group, we may as well be a little bit interactive. So actually, I'll say anything that you in particular want to see in this conversation that we're having. All right. Oh, and we have increasing our audience by a factor of like 33% or something. So Welcome, Martin. Okay, so I'm going to turn it over to Fernando now. Now that we've done a little bit of at least my motivation. So Fernando, I'll sit quietly in the audience while you take over.
So again, thank you very much, Charlie. I think this tutorial emerged out of sort of Charlie and I both looking at preferences from slightly different angles, but recognizing that there was a need for a slight twist on the way we think about evaluation. And my perspective has been over the past couple of years on preferences between rankings, and Charlie will talk about preferences between items, and Nagar will present a nice little demo at the end. So let's get started here. Just to ground some language that we'll be using today, let's talk about the information retrieval problem in the following way. So imagine I have a user who approaches an information retrieval system, and in their head, they have some information need, right? So the information need is the reason they're approaching the system. It's never observed by the system itself, but we know that it exists in there in the user's head. Now, what we do see is some expression that the user provides us of that information need. We refer to that as a query, is a short text string, and it's what the system uses in order to generate a ranking of items. So the items are this ranking is a ranking of all items in the catalog in ideally decreasing order of relevance. So the things that will be helpful in satisfying the user information need will be at the top, and those that are less helpful are closer to the bottom. Now, what I'm talking about today is, let's just say, ad hoc or single turn information retrieval. So I'm really dealing with a case where I'm observing one query spawned by the information need. So I want to point out a couple of things here. First of all, is that the system, for the purpose of this discussion, only sees the query, so this short text string. In reality, it might see behavioral information about the user, demographic information about the user, etc. But for the purpose of this conversation today, let's just focus on seeing the query, because this is traditionally how we evaluate these things, especially in academia and in research settings. Now, given that, we know that multiple information needs can result in exactly the same string or very similar query strings. And this is where questions of ambiguity arise. And so we need to be very careful when we think about a query as it being a disguise for a multitude of different information needs that might have resulted in the generation of that query. Now, I want to also talk about recommendation. And in today's presentation, we're going to kind of be talking about search and recommendation in the same breath, because for the purpose of this conversation, they are quite similar. So again, I have a user who approaches a recommender system with some information need. Now, this information need might be a desire for a new song or a new movie, and that's why they're approaching a recommender system. And unlike the search problem, there's not usually an explicit expression of that information need. It's just that they're opening up the application or visiting the website. However, unlike search, oftentimes what we have is some history of users' engagement with some items. So this might be a sequence of ratings, it might be a sequence of watches, thumbs up, thumbs down, but this is the analog of the query that we see in search settings. And like with search, given this history, we generate a ranking of all the items in the catalog. And so again, the things that are going to satisfy the user's information need, ideally rank near the top, and the things that are less satisfying should be ranked near the bottom. Now, for the purpose of today's presentation, we're going to assume a total ordering over the entire corpus, not a partial ordering, not a top K ordering. We can discuss that a little bit later, but for now, we're just going to use the mathematical convenience of a permutation of all the items in the catalog. Now, like with search, the system only observes a history, at least in the certainly in the research settings and in many production settings, even though sometimes we also have additional side information about the user, context, demographics, etc. And like with search, the same history can mask a variety of different information needs. Certainly within the same user, but even across the same users, you might have a similar history, but very different information needs. Now, the ranking evaluation problem is this. Given some observed request, and a request is what I'm going to use to describe either a query or an item history, and two rankings, pi and pi prime, determine if there's a preference between pi and pi prime. So let me first talk about how we've traditionally gone about evaluating these things and coming up with that preference. We start off by generating point-wise item labels. So given an information need and some set of items, I might generate some ratings or grades for those items. In this case, I have an ordinal rating where 5 might be the most relevant or useful item, and 0 might be not relevant at all. Now, the system might observe these ratings for a single information need. So for example, if I'm logging click or consumption behavior on some application, I know that the user has one information need and they clicked on specific items. And so I have an incomplete, although faithful representation of what the user's ratings are for those things. Or in the case of a controlled annotation study, I might have the annotators guess at multiple information needs. So for example, an annotation guideline might say, grade these documents conditioned on this query according to how popular that intent or that item might be at satisfying the information need. So that's one thing to observe. The second thing to observe is that these ratings are oftentimes incomplete. I would even argue always incomplete because we're dealing with corpora or catalogs that are usually much, much bigger than we have the capacity to evaluate on. And so definitely in production settings, we're going to see a very small number of engagements for relative to the size of the collection. And even in annotation exercises like Trek, we're not getting a comprehensive view of all the relevant items in the catalog. And so metric-based evaluation uses these point-wise item labels in order to compute what we're going to call an evaluation metric value for a ranking. And that evaluation metric value is some quantitative representation of the utility or the quality of that ranking for that information need. And so these metrics, historically developed in the information retrieval community, are usually based on either implicit or explicit models of user behavior. So if you've heard about position discounting or that sort of thing, those things are always based upon what we know about how users engage with the system. And this is a relatively classic way to evaluate ranking tasks and has been used in information retrieval for multiple decades, recommender systems as well. And you'll even find metrics like this beyond the search and recommendation community. So to go from metrics to preferences, what we do is given two rankings, pi and pi prime, we say that I prefer pi to pi prime if the metric value for pi is greater than the metric value for pi prime. Okay, so here mu is the evaluation metric. Just to go through a small exercise of what this looks like, let's take a metric such as rank bias precision, developed, I believe, a little bit more than 10 years ago now. This is a relatively straightforward model with a position discounting. So the input to the metric is the ranking pi. And what I'm going to do is iterate over the rank positions of all the relevant items. So I apologize, I didn't specify that M is the number of relevant items, and this is binary relevance we're dealing with here. And so what I'm going to do is iterate over the positions of all the relevant items, and then take the sum of the exponentiated gamma values, where it's exponentiated by the position of the ith relevant item. Okay, so this parameter gamma is really meant to model the patience of the user. And so for small values of gamma, we're going to be modeling a user that is not going to go very deeply in the rank list and will abandon their search relatively quickly, regardless of the number of relevant items that they've consumed. And for higher values of gamma, so gamma closer to 1, the user is going to be much more likely to go deeper into the ranked list. And so when gamma is close to 0.5 or so, I'm going to go as deep as maybe the fourth position of the ranking before I abandon the search. And so the focus is here really on what I'm going to call low recall. So it's not really going to go very deeply in the rank list. And to see why this matters, let's go from metrics to preferences. And as I said before, I'm going to look at the difference in the metric value for comparing pi and pi prime. And so here in the equation, I have rewritten the difference in the RBP values for pi and pi prime as a summation over recall levels, where I'm taking the difference in the exponentiated gammas. So on the right-hand side, I have a three-dimensional plot where I take an individual recall level. So this is an individual summoned in that summation. And I'm going to see, well, what is the magnitude of that thing for different values of the position of the ith relevant item. And what I see here is that for RBP value, I believe this is 0.5. Unless the one of the positions of the relevant items is essentially higher than fourth or fifth ranked position, I'm going to be contributing essentially 0 to that summation. Okay, so the differences in the summation is going to come from the highest ranked positions. So let's see why this is actually not a great thing. So for one, this top heaviness in the evaluation metrics is what I'm going to call low robustness to user behavior. In other words, the behavior of the low recall users is completely dominating that summation, so that those with higher recall requirements, i.e. those users that are more likely to go deeper into the ranked list, perhaps if they're doing a literature review or some other high recall task, are going to be dominated in that summation and essentially not going to be captured by the metric value. And so when we're comparing systems, it means that we're really going to be overemphasizing those high precision users. Now, the second issue with this is that I have what I'm calling low label efficiency. So if I've judged a ton of relevant items, it's really they're really going to waste, because most of those relevant items are going to lie in that plateau where there's relatively little contribution to the difference. And so if I'm evaluating a pair of systems, I'm not going to be using them as effectively as I could in order to distinguish a pair of systems when I want to decide which one's better. Finally, this focus on metric-based evaluation versus directly modeling the preferences results in a ton of ties, and as a result, lower discriminative power for metric-based evaluation. So in the right-hand plot, what I have is, okay, this is going to take a little while to explain. So imagine I have a pair of rankings, pi and pi prime, and pi, let's say, is a fixed ranking with the first relevant item at one of those positions, 1 through 10 on the horizontal axis. And what I'm going to do is I'm going to take a random other ranking for the same query from any one of these test collections, so robust, web, deep learning, or movie lens, and see what's the probability that the metric value, where metric value here is reciprocal rank, is tied. And so if the position of the first relevant item in that fixed ranking is 1, then the probability of tie is essentially half, which is huge. And the position, and if the position's 2, then it goes down a little bit, but it's still relatively high, and certainly higher than chance. And so what this is telling us is it's telling us that there's strong sort of like reasons behind the ties that we're observing in, say, the most recent deep learning tracks, because of the metrics we're choosing, or because of metric-based evaluation. We'll be returning to reciprocal rank later on in this part of the talk, but this is a huge problem. We're observing these ceiling effects in the metric values because we have these performant rankers, and so we need to come up with fixes for that. So I want to return to this ranking evaluation problem and now focus on this last part, which is that we want to determine if there's a preference between pi and pi prime. So far, what we've done is computed this evaluation metric and then essentially look at the values of those evaluation metrics. Let's see if we can do things a little bit differently or a little bit more directly. So in the mid 2000s, there was a fair amount of literature in the IR community that looked at side-by-side evaluation. And this was an offline evaluation method that is still relatively in high use in production environments, where they took, for a fixed query, the rankings from a system A and system B, presented them in front of assessors, and said which one is better, of course, with some relevance guidelines. Sanderson et al. Also did some work in this area. Again, always under the context of presenting these rank lists to assessors. Now, the results of these studies were that these side-by-side evaluations in laboratory settings were really nice because they were able to capture full-page utility. So instead of looking at just item at a time, you could look at the interaction between the items, et cetera, and internalized way so that the assessor could essentially say, this one is better than this other one. I don't have to explain why, or I don't need a mathematical formula for why. I just know that this other one is better. Now, what this allowed assessors to do is really capture the multidimensional notions of relevance that we often think about. So relevance is not just topical relevance. It also includes things like the diversity of the set, the authoritativeness of the set or of individual items, freshness, etc. But side-by-side preference evaluation reflects, depending on the guidelines, one of two situations that I alluded to earlier. First, if I'm just asking the assessor for their personal preference, this again is a single information need. And my evaluation will be dominated by the behaviors and the ways that our assessors are actually thinking about relevance. And so if I defer to the assessor as to what is better, I'm really going to have a very specific notion of what relevance is or what a preference is. On the other hand, I might have a set of relevance guidelines that ask the assessor, as I said before, well, try to capture the general user and give a preference for, say, the average user. And in this case, I've pushed the modeling effort into the assessor's head and really asked them to do to come up with a personal model for the general population and their preferences amongst users, amongst rankings. Now, there's a few drawbacks to this approach. So first, in order to compare a pair of systems, I need to do a brand new user study. Secondly, these labels, well, it's great that they're capturing these multidimensional notions of relevance. They're not really gathered in a naturalistic environment. So we're not, when we're interacting with systems, we're not seeing a pair of rankings and then deciding to opt for one instead of the other. We're looking at a single ranking. And so there's some risk that when asking assessors for judgments through this artificial interface, that they're giving us something that isn't quite an accurate reflection of the true preferences if it were provided in the real interface. So one question we might ask is, can we actually derive preferences between rankings in a production setting? And I'm not going to spend too much time talking about interleaving, but the answer is yes. So interleaving is a method that was developed in the early 2000s for doing what I'm going to call online side-by-side evaluation. And so the objective is the same as I had in the offline side-by-side evaluation, which is given a request and two rankings, determine which one's better. But the problem here is that I can't present a side-by-side a pair of rankings to a user because it really disrupts their experience. It breaks a lot of things. And so their information seeking task might be disrupted if I were to ask that. And so the approach to gathering preference information that we want to take is one that disrupts the user interface as little as possible. So again, consider my user who's approaching the system with some information need. And I have these pair of rankings from two systems, A and B. Now, of course, I can't present both of them to the user for the reasons I gave earlier. So what I want to do is find some way to combine them into a new ranking that I would then present to the user. And the method developed by Joachim's in the early 2000s is the following. So I'm going to compute this interleave ranking by doing the following. First, I'm going to initialize the final ranking to empty. Then I'm going to flip a coin and pick between A and B. So A on the left, B on the right. Assume I pick A for the purpose of this explanation. What I'm going to do is I'm going to pop the top item from the, in this case, list A, and I'm going to add it to the bottom of the interleave list. Then I'm going to pop the top item from B and add it to the bottom as well. I'm going to repeat this over and over again, so steps 3 and 4, until I've exhausted the rankings A and B. And so what this does is it essentially zips together the two rankings, but there's some randomness in terms of which ranking has preferences here, i.e. which ranking is at the top of the starts first. Okay, so what we do is then present the interleaved ranking to the user in production, and then observe which items the user will click on. Using the clicked information, I can then derive a preference from between the pair of rankings based upon which item the items the source of the items that were clicked upon. So this interleaving method is highly correlated with both offline and online metric-based preferences, which is good. Moreover, interleaving in these sets of experiments really demonstrated that preference-based evaluation can get much more granular than metric-based evaluation. That is, when I observe a tie in metric-based evaluation, so i.e. what I was observing with reciprocal rank earlier, preference-based evaluation can actually differentiate between those systems. Now, secondly, and partially because of this granularity, it's much more sensitive. So I'm able to predict the true system preferences with much less data than metric-based evaluation. So I have a citation here at the bottom of really, really nice, comprehensive summary of the results for interleaving, again, in an online setting. Now, a few comments. So first, interleaving preferences reflect the person who's clicking their personal preferences in terms of depth that they're willing to go, types of documents they're going to click on. And as a result, when I'm aggregating across users, this aggregation is really going to emphasize the dominant preferences, i.e., for example, top heaviness that I observe in users. Now, that's an issue that I'll come back to later. But moreover, there's other issues here. So, for example, the data are difficult to reuse. So, for one, because I'm gathering these labels in a production environment, they're quite sparse. So, I'm only going to get clicks for things that the user sees. And secondly, this data can't be reused, i.e., new rankers have to be put into a new interleaving experiment, and then and preferences derived from those clicks. So I want to step back a little bit and think about our what I'm calling an evaluation desiderata. So what do we want from an offline evaluation? So for one, we'd ideally want it to be offline. In other words, we want to compare systems without potentially putting real users at risk, right? That's not the complete way of how we evaluate systems, but it's a really important one that we do before we actually launch something in production. Secondly, we'd like this to be reusable. So we want new comparisons to be possible without generating a ton of new data, as we had to do with the previous two methods. Third, as we noticed with interleaving, explicit preference modeling is quite important and can add granularity and sensitivity to the evaluation. And so we'd like to preserve some of that. And finally, and I brought this up a couple of times, what we would like to do is be robust to the different ways in which people might be engaging with the system. I want to be robust to those users that are looking for one relevant item, as well as to those users that are looking for the complete set of relevant items. Now, unfortunately, all of the evaluation methods that I've seen so far have not satisfied this. And just as a summary, we have metric-based evaluation, side-by-side evaluation, interleaving evaluation here in a nice chart. And what we see is none of them satisfies all the criteria that we're looking for here. And certainly none of them satisfies this unbiasedness that we desire. And what I want to spend the rest of the time talking about is a new way to evaluate systems based on preferences that satisfies all the desiderata that we're searching for. So the first work in this series was published at SIG-IR last year. And the first part of this presentation is going to be really digging deep into what was happening there. I'm also going to be presenting a couple of new results that are currently on archive or under review that are extensions of this that are quite nice theoretically and also empirically. So returning to this desiderata for preference-based evaluation, let's talk about how we're going to address these things. So as I said before, we want things that are offline and reusable. We're going to satisfy that by reusing point-wise label data. So Charlie and Nagar will be talking about preference-based label data later on. But for the purpose of this part, let's just focus on the point-wise label data that we're used to collecting. Now, secondly, what we want to do is explicitly model these preferences. And to do this, we're going to define what we call a preference function in the subsequent slides. And then finally, what we want to do is be unbiased in the different ways in which users might be engaging with the system. And we're going to do this by, instead of being top heavy or really favoring some dominant user behaviors, we're going to try to be robust to the diversity of sets of user behaviors that I can observe. Okay, so let's do a little warm-up exercise. So consider a user who's interested in exactly one relevant item. And I have these three pairs of rankings, and I want to understand which ranking is preferred in each situation. So in these rankings, the white items are non-relevant and the red items are relevant. So in the first pair of rankings, again, if the user is interested in exactly one relevant item, we know that the user in condition A, in the ranking A, will have to go to rank position 2, whereas in the ranking B, they only need to go to rank position 1. And so, assuming that users with that recall requirement prefer things that are closer to the top, I would say that I prefer B to A. Now, in the second pair of rankings, I've moved those relevant documents up from the bottom for ranking A. And again, I'm going to have the same user who's interested in one relevant item. And if they're interested in exactly one relevant item, though that movement of the relevant items up for A should not matter because they're satisfied after the first relevant item. And because, again, it's still at the second rank position for A versus first rank position for B, I'm going to say that that user is going to prefer B to A. And then the third pair of rankings, I've moved that top rank relevant item for A up to the top position. And the user who's interested in exactly one relevant item in this case will have equality because they have to go through exactly the same number of relevant items. They don't care at all what's happening below that relevant item. And so we say there's equality here. Now let's think about the user who's interested in exactly two relevant items. In the first condition, I see that in order to get two relevant items, for both rankings A and for rankings B, the user has to go down to rank position 5. And so in this case, I would say that they're equal because the position of the higher rank relevant items are irrelevant. They only care about how deep they have to go to satisfy their recall requirement of 2. Now let's look at the second pair of rankings. In this case, for ranking A, the user only has to go down to position 3 before they're satisfied, whereas for ranking B, they have to go all the way down to ranking 5. And so what I'm going to say is that this user would prefer ranking A to ranking B. Now, even if I move the item up from the first relevant item for A from the second rank position to the first rank position, I'm going to say that the second rank relevant item is higher for A than for B, and so I'm still going to prefer A to B. Okay. And so this suggests one way of evaluating systems based on something I'm going to call pseudo populations. And these sort of populations are going to be like groups of users that I want to be robust across. Based on the warm-up exercises we just did, the populations I'm going to be thinking about today are based on recall levels, so possible recall levels. So the number of relevant items people are actually interested in. Just to go a little bit deeper into this, again, I imagine a user with some information need, and the user interested in one relevant item will prefer B to A in this case, A to B if they're interested in two relevant items, and A to B if they're interested in three relevant items. And so all these are possible user populations that I could that could be generating that query. And so I want to consider all of them before actually computing my preference. Now, how we're going to do that precisely is in the following way. So I'm going to find a new evaluation method that I'm calling recall paired preference that is a function of two rankings instead of one, as I observed in the metric-based evaluation. And for this pair of rankings, what I want to compute is the expectation over possible recall levels I that a user with recall level I will prefer pi to pi prime. Okay, and how am I going to do this? Well, what I'm going to do is go through the process I went through in my warm-up exercises and in the previous slide. Is I'm going to iterate over all of the recall levels and just look at and just compare the rank positions of the ranked relevant item. So I'm just going to compute the expectation over this sine function of the difference in the rank positions. Now, because it's an expectation, we say that there's some probability of observing this recall level PI. And because we're interested in fairly dealing with all the possible recall levels that the user might have, I'm going to say that's uniform. Okay, so I say that a ranking I is better than ranking, ranking pi is better than ranking pi prime if for across all recall levels, uniformly weighted, it's preferred. Okay. Now, I've said uniform so far, and this suggests that recall paired precision is an average case preference between two rankings over the set of user populations defined by recall levels. Now, of course, because pi I can be defined in lots of other ways, we can also explore different ways to weight the recall levels. So, for example, we could weight it according to the reciprocal of the recall level, and we get reciprocal rank style weighting of the recall levels. Or we could weight it according to something like a DCG discounting, again, based on recall levels here, not on the positions. Now, what does this result in? So in the left-hand table, we have observed that recall paired preferences, both in its vanilla form as well as in its weighted form or its non-uniform form, is highly correlated with existing evaluation metrics, which is great because it means they're measuring something quite similar to what we have been measuring over the past few decades. That said, it's much higher in terms of statistical sensitivity. So here I'm using Sakai's discriminative power method to essentially compute the percentage of pairs of systems for which I observe a statistically significant difference. And in this table on the right-hand side, we notice that RPP as well as its variance are much more sensitive to differences in systems than classic methods like average precision, NDCG, and definitely reciprocal rank. Now, I described RPP as average case performance, and so I did so because partially because we can think about alternative ways of aggregating those preferences. So we can think about best case performance as being the preference across the top ranked relevant item. So here I have it in mathematical notation. I'm saying that system pi is preferred to pi prime if the rank position of the top ranked relevant item is lower or is higher, i.e. the rank position is lower than or smaller than the rank position of the highest ranked relevant item for pi prime. Okay, so as you might have guessed already, this is equivalent to saying I have a preference if the reciprocal rank for pi is greater than reciprocal rank for pi prime. Okay, so that's nice. It means that best case preference is exactly reciprocal rank, and reciprocal rank is a subversion of best case preferences. But there's some drawbacks to looking at best case preferences, of course. So recall from this plot earlier in the presentation that reciprocal rank, i.e. best case preferences, is subject to a ton of ties, especially for highly performant systems. And again, I'll point you to Voorhees et al. From last year's SIG-IR that noticed that these neural rankers were getting a ton of ties, partially because they're bringing all the relevant items close to the top. So best case performance, while theoretically interesting, is not really practical because of so many ties. So one way around this is to define what we're calling lexicographic precision. And so the way I'm going to define lexicographic precision is in the following way. When I'm comparing two rankings, instead of just looking at top rank position, when I observe a tie in the top rank position, I'm going to back off to the second highest rank, top ranked relevant item and compare those. And I'm going to iterate down the ranking until I observe a difference. And when I observe a difference, I'm going to say that's the preference between a pair of rankings. Now, this is really nice because it gives me a total ordering over all permutations of relevant items in the corpus, which means I'm going to have very, very high discriminative power and very few numbers of ties. Just to give a little sense of what this looks like, here's pseudocode for lexic precision. Let's step through it a little bit. So I'm going to iterate from top to bottom. So that's that line 2. I'm going from the top recall level down to the last recall level, M, where M is the number of relevant items. And I'm going to look for differences in the reciprocal rank. So that's line 3. So if there's a difference in the reciprocal rank, i.e. it's not 0, I'm going to return some value. And I'll come back to that in a little bit. If I iterate over all the recall levels and never observe a difference, I'm going to return 0. In other words, there's no difference in this performance. There's no difference in the preference. And this will only happen if both rankings put relevant items in exactly the same positions. Now, it's not the exact relevant items, it's just any relevant items, but they're in the exact same positions. Now, coming back to this quantify preference thing, what I'm going to do here is I'm going to return the magnitude of the preference. So this could be something like I did in RPP, which is just a sign function and say that I'm going to return 1, -1, or 0 based upon what the difference in those rank positions are. Alternatively, what I can do is I can actually return the difference in the reciprocal rank for that recall level as my magnitude of the difference in performance. Just to go through this intuitively, let's assume I have these two rankings, A and B. Again, red is relevant, white is non-relevant. The way we compute lexi precision is to start at the top. So here A and B have exactly the same position for the top ranked relevant item. So I'm going to go down to the next one. Again, I have a tie for recall level 2. So I'm going to go down to recall level 3. What I observe here is the rank position is higher for A than for B, which means then that I prefer B to A because the top ranked relevant item at recall level 3 is higher. Now, the results are pretty similar to what we saw before. So on the left-hand side, we see that compared to reciprocal rank, Lexi precision in both variants has much higher discriminator power. It's able to, because it's not tied so often, distinguish between a pair of systems. And on the right-hand side, it's worth, let me pick through this a little bit. So on the horizontal axis across all these plots, I have the fraction of labeled items that I'm preserving. So on the left-hand side, I've dropped out up to 90% of the labeled items and left them unlabeled. On the right-hand side, I recover up to 100% of the labeled items. The green line is reciprocal rank, the red line is Lexi precision. And what you see is that as I have more and more labeled items, the probability of a tie actually goes up very quickly for metric-based evaluation with reciprocal rank. This should be very scary because it means that as I get more and more relevance judgments, and we notice this in the deep learning track, I'm getting a bigger and bigger probability of a tie, and therefore a lower ability to distinguish pairs of systems. Now, I talked about best case performance. We can also talk about worst case performance. So now here, when we talk about worst case performance, instead of looking at the top ranked relevant item, I can look at the bottom ranked relevant item. So the notation here is exactly the same, except instead of subscript 1, I'm using subscript M, which is the number of relevant items. And I infer the preference based on the position of the bottom ranked relevant item. Now, if you thought things were bad with reciprocal rank, they're even worse for worst case analysis because most systems don't retrieve all of the relevant items. And when you don't have all the relevant items, it means that the bottom ranked relevant item, if we use a conservative way of estimating its position, will be tied. And so this worst case analysis is not great, but if we use the intuition behind lexicographic evaluation, we have a way out. So Lexi recall is exactly the same thing as Lexi precision, except what I'm doing is I'm moving from the bottom up. So the iterator in line 2 is going from M to 1 instead of 1 to M. Line 3 is exactly the same. And then line 4, instead of looking at this quantify preference, I'm just going to return the sign function every single time. And so to walk through this again with the same two rankings, I start with the bottom ranked relevant item. They're equal in these two cases. Then I look at the next to last relevant item. Again, they're equal. And then when I get to the third to last relevant item, I notice that the third to last relevant item is higher in A than B. And so I say there's a preference of A over B if we're looking at recall. And the results are similar here. Again, on the left-hand side, we have the result that harkens way back to interleaving, which demonstrates that preference modeling gives me higher statistical sensitivity than existing recall-based, recall-oriented evaluation measures. And on the right-hand side, I apologize, the rows aren't labeled here. The top one, I believe, is news, to the News Corp Refer Trek. The middle one is the Web Corp Refer Trek, and the bottom one is the Deep Learning Corp Refer Trek. And on the horizontal axis here, I have the number of labels removed. So I apologize that this is reverse of the previous plot. So on the left-hand side, I have 0 labels removed, and on the right-hand side, I have almost 100% of labels removed. And what we notice is as we're removing labels, all of the metrics, of course, will start to degrade, so you'll start to observe more ties. But the number of ties that you're observing with classic recall-oriented metrics, so recall at 1000 or R precision, is going up very quickly. So one thing that you should take away from this presentation, if nothing else, and if you don't even think about preference-based evaluation ever again, if you're dealing with sparse labels and you're looking at recall evaluation metrics, I would be very suspicious of R precision or recall at 1000 because I'm observing all these ties. The statistical sensitivities can be way down. And if you look at the longer version of the paper, the ability to predict the true preference in terms of recall is quite low for these metrics. So I want to close this part of the presentation by just summarizing quickly. So preference-based evaluation is primarily motivated by directly modeling the thing that we're actually trying to do in our evaluation, which is preferences, right? And as a result, we are much more sensitive in terms of what we can detect in terms of system and ranking differences. The theoretical connections to best and worst case evaluation is actually, I mean, from a theoretical perspective, quite interesting, but also allows us to design new precision-oriented and recall-oriented evaluation metrics that are much more sensitive than what we have right now. Moreover, this explicit model of different user populations, at least as according to recall levels, is quite nice because we can manipulate this probability distribution and sort of like aim our evaluation metrics in different directions. Few extensions that I think are worth looking into. So first of all, I spent all my time talking about ranked lists, and we know that modern search and recommendation systems deal with much more than ranked lists. And so extensions to this to grids or to sequences would be quite interesting. Graded relevance and diversity are two things that I didn't touch on in this presentation, but are things that if you look at the Cigar paper from last year, we dealt with, but I do think that there's some work to be done there. And although it's one little word at the bottom of extensions, I do think that the most exciting thing here is how we use these approaches to directly optimize our rankers. The fact that they're more statistically sensitive means that we may be able to optimize with less data or more precisely across these populations of users.
Okay, so what I wanted to do is Fernando had this lexicographical example, which I haven't seen, because as you can see, the slides we're working with don't have the example. But he had the example where there were two rank lists, A and B, and he had a bunch of squares like this. Yep. Okay. I have to talk. I have to do my best Frank Sinatra and like talk into the microphone directly. So we had rankings A and B, and we had things like this. And he had these two things as relevant. And I think there's some things like this. And he said, we're going to not worry about those because those are tied in relevance. And we're going to trying to compare lists A and B here. So we'll move down one level. Okay, so this is relevant here. So that means that A is better than B. So that's one solution to the problem. The solution to the problem is to go a little deeper. The solution we're going to look at now is to look at these two things here. Now, if they're the same item, we can't do much. They're the same item. But in fact, they may not be the same item. And as I started, some of you weren't here for my warm-up example. Maybe I'll go back to my warm-up example. That if these are different items, we can now, even though we apply our relevance guidelines and we say, okay, they're both equally highly relevant or perfect or something like that, why don't we ask a person, you know, which one is better? And if we ask a person, or we look at online signals, or we ask a large language model, or we do something to figure out which one is better, then we can actually determine that which of these is better without having to go deeper into the list. So that's the key difference between the first half of this and the second half of this. The first half of this is focused on, we have two rankings, how do we figure out which one is better? The second half of this is more focused on the fact that not all perfectly relevant things are equally perfect. And since it was early in the morning and not everybody was here, I will go back and you can see that I'll go back to my warm-up example that I started back here. Sorry, here's my warm-up example. So this is, I mean, it's been a number of years now, so I can talk about it, but I was at Facebook for about 2.5 years. And during that time at Facebook, we rebuilt their search metrics stack. And this is an example that always struck me, and I love to show it off. This is, you guys remember this guy. Hopefully we'll never see him again, but you never know. Okay. And if you query Trump, here are 2 pages that at that time, long ago, could come back in response to Trump. And if you're used to doing search evaluation offline or online, if you're doing it offline, you write what these are called relevance guidelines. And for Google, they're maybe 300 pages long. You can go see them online, okay? And no matter how you write those relevance guidelines, no matter how you define perfect or highly relevant or anything like that, both of these results are perfect. Okay, this is both these blue tick marks. You didn't have to pay $8 for them. Okay. They say that these are official pages. This is as president. This is as not president. Whatever guidelines you have, these are both perfect. When I put them side by side, though, I can write guidelines that say that the one on the left is better. Sorry, the one on your right is better than the one on your left, because we can compare followers. We can compare the fact that some people that I know like this page, follow these pages. And so it's easy to write guidelines that say that the one on the right is better than the one on the left, that this result is better than this result. But you can't write those guidelines unless you can put them side by side. You have to have some basis for comparison. And that's really the inspiration of when I left Facebook. I came back to academia and I said, we have to figure this problem out, because it takes some thinking and it takes some research. So now I can skip through Fernando's slides, or partially written slides. You can tell it's a tutorial because we were finishing the slides last night, right? Or he was finishing them yesterday morning and we were finishing them last night. So I want to talk about preferences between items. That's what I'm going to talk about for the next half an hour, and then we'll do a demo of some things after the break, and then I'll keep talking. So basically, I'm just going to check my time here to make sure you don't miss coffee. So preference between items, what we just saw, basically we're going to do our evaluation on two factors. Basically, is item A an appropriate response? So we look at this here and we say, is that appropriate to the question or the relevance need? You have to do that, because if you're going to put things side by side, and I say, where's a good vegetarian restaurant in Singapore? And I get a vegetarian restaurant in Kuala Lumpur, and I get a dog groomer in Melbourne. Neither one of these are related at all. I can't put them side by side and compare them. Okay. So the first question you have to ask with any item is this a good response or not? And if it's a reasonable response, then we can put them side by side like this here, or like we just saw, and we can say which one is a better response, or possibly equally good. So we have basically binary judgments that we're going to make about the items, okay? Which are in many ways, once again, I want to go back, maybe most of you have never written graded guidelines, but writing guidelines that have relevance grades in them, that generalize. This is almost an impossible task. So as I said, number one is appropriate because comparing unresponsive items is just a meaningless act, right? I want a vegetarian restaurant in Singapore, comparing a vegetarian restaurant in Kuala Lumpur to a dog groomer in Melbourne. What does that mean anyway? Okay. And we get either A greater than B, A less than B, or possibly A equals B. And so now we have these rankings here. How do we get to comparing rankings and therefore rankers with these labels? Okay. So these preference, and I'm going to emphasize, these are not necessarily preference judgments or preference labels. You can, in fact, do them side by side. So we can actually put a assessor in front of these things and say, here is a query, vegetarian restaurant Singapore, or it could be recommendation. Doesn't necessarily have to be a query. I pull my phone out and I say, I want to go to eat somewhere, and it says, here's a restaurant to go to. Okay. Or so we can get them from human judgments. They can be crowdsourced or they can be authoritative. And I'm going to make a distinction here. Crowdsourced means all of the things associated with crowdsourced workers. So they're trying to do the task. I don't want to be unfair to them. If you're a crowdsourced worker, you're trying to do the task as fast as you possibly can so that you can do more and more tasks, right? Authoritative means it's your job. We're going to train you. We're going to give you guidelines. We're going to teach you how to do this. And your job is to do a good job, not to do an okay job of a lot of tasks, but to do a good job of a fixed number of tasks. You can infer preferences from online signals. We saw some interleaving. You can also look at items. So basically, if I skip an item, in a result, if I skip either recommendation or search, if I skip an item, that gives you a preference label. Okay, it tells you that the thing you skipped is not as good as the thing that the person clicked. And you can also consider external factors with preference judgments. I would prefer a vegetarian restaurant in Singapore to one in Kuala Lumpur. I would prefer one in the Raffles Center across the street, perhaps to one in the north part of Singapore, right? In news search, we would prefer the updated recent articles. And in social media search, as we saw from my motivating example, we can look at friends, we can look at other social signals to pick a result. And these kinds of things can be applied either automatically or it can be applied by the assessor. The assessor can trade off, you know, your friends like this place, it's close by versus it's the most popular thing. So that you can actually train people, I think, to make these kinds of decisions. Okay, let's make sure we know what problem we are trying to solve. So I have to ask this question because it's a relatively small group of people, and apart from Nagar and Martin, I don't, and my colleagues from Waterloo in the back, I don't know any of you. So do you know what I mean? I just want to find out. So who knows what I mean by graded assessment, like NDCG? So you know what NDCG is, you know what Martin, probably you do as well, right? I would guess. Okay. So basically the idea is we're going to take our search result here, okay, or our recommendation result here, and we're going to ask a human assessor to rate on a Likert scale how good that is. So we actually hire, I don't know, large numbers of people at different search companies, recommendation companies to apply to label these kinds of results. And if you are a person that has been involved in defining these grades, they are nearly impossible to write in an industry context. Maybe within the web search community, this is wisdom after all. Maybe within the web search community, we have a pretty good idea of what a good web search result is. But when you move to social media, when you move to e-commerce, when you move outside the domain of web search, writing these kinds of guidelines is an exhaustive task that, you know, you have program managers who spend their lives trying to get these right, and they never get them right. Within these kinds of evaluations, there's completely inconsistent terminology. You know, I went around and we get perfect, we get moderately meets, we get relevant, we get related, we get not relevant. There's a whole bunch of language and nobody knows what these mean. We need a lot of training to apply them consistently. And I mean this really, like, there are whole teams at companies who do nothing but try to get people to apply these grades consistently. And then after we have these grades, after we have these things that we sweated to make that fine distinction between perfect and highly relevant, we do, in order to compute metrics with these, in order to do the thing that Fernando alluded to earlier, and we have to compute a metric across these things, we magically take the number, the word perfect, and we turn it into 31/32. Or we take highly relevant, we turn it into 15/2. We just magically map it to some numbers, add things up. And so that's one problem we're trying to solve. That this whole process of doing relevance grading and offline evaluation, basically it does work. I know it works at Bing. I know something similar works at Google, places like that. But for any kind of search outside that domain, it's not clear that it really works. On the other hand, if we're doing online metrics, they are difficult, as Fernando said earlier, to compute counterfactually. Okay. And one of the problems is that a high NDCG value, a high offline search metric, does not necessarily correlate to more clicks or more interactions, and vice versa. So nobody understands the relationship between them. So preferences, at the very least, is something you can take in lots of places. Okay. So this is the problem we're trying to solve. That basically we're really in a very primitive era still for search evaluation, for recommendation evaluation, for question answering evaluation, except suddenly in actually building these systems, we are not in a primitive era. We have made huge leaps in the quality of the results. And now you get a result like this. Everything, in a lot of cases, is just highly relevant, right? All of the results look really good. And so now how do we make these fine gradations between judgment levels? Don't worry, I'm watching your coffee. Okay, no worries. You'll get your coffee. All right. So I just want to do a reminder. I stole these slides from Wikipedia. Who has seen this formula before? I just actually want to check because, okay, most of you have seen this formula. These are the relevance grades, so these are the perfect. Does anyone understand the motivation behind the mapping from perfect and highly relevant things like that into a gain value? Does anyone understand the rationale behind that? Martin, would you like to explain the rationale behind the mapping of relevance grades to gain values?
Some picture of the user time and effort that the user did.
Right. Great. Yeah. And I think that is basically the rationale I have in my mind, and the rationale you have in your mind, and the rationale that everyone uses that this has in their mind. Oh, I'm sorry. Martin, can you give a summary of that one sentence?
Like I just said, but seriously, so you're trying to understand and model how much effort someone is putting in by having to go down the ranked list, and what he or she gets back by examining useful results, by getting useful results.
Great. So, but if I map highly relevant to 7, and I map perfect to 15, what does that mean? Yeah, I don't know either. Nobody knows. It's this magic that we do that is intended to give us a number that we can sum up. Okay. And other things, Fernando had something called rank bias precision. That's another model of somehow the benefit that the user gets, but these are not tied to any reality. Nobody sat down and said, okay, yes, if I get a highly relevant thing, that's going to give me a 7. And if I get a perfect thing, that's going to give me a 15. Nobody knows what this means. Okay. And, so we don't know. One of the ways we think about this is maybe if we map the gain into a number between 1 and 0 by dividing by 2 to the maximum gain, we might think of that as the probability that if you see it, you find what you're looking for. But that's just lies that we tell ourselves. Okay. And in fact, there's a really good paper that was in TOEIS 2017 that basically looked at, I'll come back to this paper very briefly later, but basically they said, yes, this is nonsense, right? There's no possible way to map the variance in human perception to relevant scales. And in particular, the selection of this mapping, which could be linear or exponential, is basically does not work universally, does not make. So it's not just I'm sitting here and saying this doesn't make any sense. There's been a lot, there's not this and other work that we put in our bibliography that says this is just not a thing that's going to work. Okay. And then here we go. This is track conversational track. Who is familiar with this? Maybe I think you guys are maybe familiar with track conversational track, right? This is 2020, and it uses NDCG as the primary measure. Here are the entirety of the guidelines. So if you're going to apply guidelines for Trek 2020 CAS, here are the definitions of what they mean. These aren't too bad. I mean, industry ones will have hundreds of pages in them. Okay, these aren't too bad. Okay, so you can maybe believe a crowdsourced worker will read these. Yeah, not really. Right. And crowdsourced workers never read any instructions, as far as I can tell. They just go to the task, and if they can't figure the task out, then they come back to the instructions. Okay. We did a lot of crowdsourced preference judgments over the last 3 or 4 years. Here are the entirety of the interface. This is the interface we use for crowdsourced judgments. This is just to make them feel better, right? how is the Never-Ending Story film received? And you pick the one you want. And that's the entirety of, you have now been fully trained on this task. Okay, you have been fully trained on a preference judgment task. You could do this now. This is actually kind of hard. Never-Ending Story film received. Can people read this? Yeah, which one do you like? Who says the one on, what is that? The one on your left. Who likes the one on the left? No one likes it. I'm paying you 15 cents for this, 25 cents for this, 25 American cents to pick one of these. Left. Anybody else got a different answer? All right, Martin, I wish I had 25 US cents. We could give you, that's how much we pay for one of these, by the way. We pay 25 cents, which our ethics people, tell us is minimum wage for these kinds of tasks. So that's what we pay. But that's the entirety of the relevance guidelines. Whereas if I ask a crowdsourced worker to do that, they will ignore me and just pick something at random. Okay, so advantages of the preference labels as opposed to judgments. There are multiple sources, explicit or implicit. It's basically binary, so we don't need to make up what the levels mean. It's just which one do you like, or maybe you like them both equally. There's less need for complex grading guidelines. And basically, if your searcher likes this one better than that one, I can encode it directly. I like that better, right? Actual human need, I like that one, is encoded directly. Okay. So if we want to do this, though, we got a bunch of problems to solve, which have basically hampered progress in this area, because people have been thinking like we are thinking now for the past 30 years, that, hey, a preference would be a good thing, okay? One of them, people go, well, I don't know, if I ask people, is it really transitive? I don't know. Is that even important? But it's something that people go. And the other thing people worry about is that, like there's n log n of these preference labels. If we don't have transitivity, we're going to have to ask like huge numbers of questions about which is better than which, right? And we also have no way, Fernando was talking about going from a preference to a number. We have no really established method to go from a preference to a number, okay? So before I get to that, now you've seen Fernando, now you've seen me. We're 10 minutes from a coffee break. Do we have any questions at all? Get us started, Martin. Come on, I got you back there. Oh, sorry. Yes, I'm sorry. I get Martin his own mic because I'm calling him.
There's a fair bit of theoretical work in the sort of decision-making literature on the agent-based modeling on preferences, different types of preferences, different assumptions about the order of preferences. For instance, this first question, this would typically be something they would look at, but also the second and third. Do you guys connect after the break to some of this literature? Oh, great.
Mostly we're looking at the IR focused literature, but we've gone into more of the rest of the literature as well, right? And I bring these up, because these are the ones I hear from people, right? These are the ones that pop to mind, and we want to look at it a very practical question, rather than philosophical. We're going to actually test this, right, and see if it applies. Yeah. I think that's okay. So I do want to go back within IR to look at some of this. So here are 3 papers. Now, these are papers, I would assume that no one here, except perhaps for Martin and myself, were born when these papers were written. Okay. But I'm pretty sure that's true, actually. But back 30 years ago, people were talking about, within the context of information retrieval, that we should base evaluation on preferences. Now, around about this time, various evaluation exercises appeared, TREC most notably, and they were based on point-wise judgments of individual items in terms of relevance. So this stuff got kicked away. Ben Carteret, who knows Ben Carteret? He's of course, Ben Carteret, and my my person who didn't realize he was going to be roped into the actual tutorial itself. Martin back there knows Ben Carteret. So Ben Carteret is a director, one of the directors of research at Spotify now. And about 10 years ago, actually about 15 years ago, he spent a lot of work working on preference judgments in the context of search. And a lot of what I'm going to present today is not, I'm not going to present these papers, but I'm going to actually be building on this. This is very significant to what we're doing here. And then some very recently, there's been a bunch of papers over the years. I highlight two from the last year or so. Tetsuya Sakai's group in Tokyo and Yichun Liu's group in Tsinghua have done some really interesting papers. And there's a whole bunch. We have a whole bibliography, I don't know, 150 papers or something in the paper associated with this tutorial and a review of all this stuff and in the associated papers. So I just want to say this is something that people have been thinking about for a very long time. We are going to, and here are 3 papers that I've written with Nagar and some other students. So we're actually going to spend most of the rest of this segment of the tutorial looking specifically at the things we've been doing as an example, but I want to make sure people understand that there's a very long history. There's hundreds of papers over the years trying to make this work properly, and a lot of evidence that there's something there, but it's hard to make the pieces all come together. And I don't think we would really worried about this until we've hit this sort of neural error where everything is practically perfect, right? Like, I guess I should have said that earlier. The Mary Poppins results practically perfect in every way, right? Jokes at the wrong part. It's 9:54. I'm going to make it a little ways into the next part, and then I'm going to let you have the coffee break, and then we can come back and talk about some. But I actually just want to end by talking a little bit about, so what we have now is somewhere we've gotten huge numbers of preference labels. Okay, we don't know where we got them from, but we got them either from judgments, crowdsourced judgments, authoritative judgments. We inferred them from online signals. We asked ChatGPT which one is better. We did something to get these relevance labels. Okay, what do we do with them? So there's been a bunch. I said that a few seconds ago that one of the questions was that there are evaluation measures proposed but not standardized. Okay. A lot of these are either based on counting discordant pairs. So you say, well, here's a ranking. How many, we know preferences, how many are flipped in this ranking? The problem with that, all those metrics really suffer from the fact that most of the preferences are not in the ranking. So very hard to measure. The other one is based on, a very common is converting preferences to gain values. But once again, we somehow have to magically turn a label into a number, and we don't really know how to do this. So what we're going to do is we're going to basically base the metric I'm going to spend a lot of time on today on number 1, but we're going to basically say we're going to 2 rankings. We've got 2 rankings, A and B. What I'm going to do is I'm going to find a rank similarity measure. I'm going to use something I'll come to called RBO. That's what I'm going to use for my rank similarity measure, but there's a bunch of rank similarity measures. Okay. And the basic idea of how this is going to work is I really wish I had a microphone that I could wear instead of, so I'm going to put this down and draw a picture. So this is our rank similarity measure. I know people can't hear me. So I'm going to make a set. I'm going to make a set, and that set is a set of ideal rankings. Okay, so this is a set, and I'll show you where these sets come from. Okay. This is the thing we're trying to measure. Okay. So this is something generated by a search system, by a recommendation system, by a question answering system that we want to measure how good this is. Okay. So what we're going to do is we're going to find somewhere in here, there really should be one on the edge, actually. We're going to find one in here that's closest to the ideal ranking, and we're going to do a rank similarity measure between those two. And the closer it is, the better. So if we're close to this edge here, right? So yeah, this should be, there's one here. It's going to be one on the edge. The distance between these two, this is how good you are. If you're one of the ideal rankings, you're one. The farther you get from this, and it's an actual metric, you know, mathematically, the worse you are, the farther you are away. And the reason we don't say take an average or something like this is because actually there can be a huge number, millions of these. I'll show you in a minute. There can be millions of these. We take the closest one because that's how far you are from being inside the ideal set. Okay. So that's our plan for all our evaluation measures. Is this plan? There's actually huge numbers of measures we could use here, but the one that we use is rank bias overlap. William Weber, Alistair Muffet, and Justin Zobel, I think, might have done this. I know for sure it's Alistair Muffet and William Weber. And this is a rank similarity measure that supports indefinite rankings. So I lost my other picture, but we can stop it at any point. If we don't know what's far down here, we're okay with that. It's top weighted, so differences at the top are more important than differences farther down. And it supports incomplete rankings, so you can have items that only appear on one list or the other list. And basically, here's the formula. We don't want to get into it too much. This is a persistence parameter. Earlier in this talk, this was a delta. You can see that Fernando and myself and Nagar did not quite get everything aligned last night. But this is based on the rank bias precision measure that he showed earlier. Okay, and basically this is the overlap between the rank lists. Here are the rank lists S and T at depth TD. It's very, very simple measure. And it's a metric in the mathematical sense. There's a lot of good theory behind it. It's well established. So between these two slides, this one and this one, this basic procedure, that's how we're going to measure. That's what we're going to use for the replace NDCG. It's this thing, we call it compatibility, just because we need a name for it. Okay. 10 o'clock, so I'm going to go one more slide. So we're going to look at three kinds of compatibility. Compatibility with ideal rankings that are based on graded judgments. Okay. So I said graded judgments, hard to do, hard to produce, but the real problem with graded judgments is the translation to gain values, which is completely meaningless. So instead of that, we're going to compute compatibility based on graded judgments. We're going to do compatibility with ideal rankings based on, so basically what we're going to do is we're going to specify the top K of what the ideal ranking should be and just measure from that. Okay, and we're going to use human judgments for that. And we're going to basically then go all the way and say, if you just give me an arbitrary multi-graph, directed multi-graph of preferences, I'm going to be able to compute this measure. There's some NT complete thing in there, but we'll see how we resolve that problem. All right, so before I hit that, it's 10:01. I'll be here. We got a break now. We can network for a half an hour. So come back though, please, at the end of the break at 10:30. And we'll show you some magical things that we've been able to figure out. And we'll also do a demo. To remind you what we're doing, some of you are new, right? There's not, welcome, right? Some of you have gone. Lost some people, gained some people. What we're doing is we're talking about, these are rankings, A and B. We're trying to figure out, okay, they're returned by something, recommendation system, whatever. We're basically trying to assign a score to how good this is so we can compare it, tell us how we did it. And basically the theory is that, and I was talking about this is actually, I redrew these pictures. I apologize for my horrible handwriting, but my grade 1 teacher couldn't do anything about it either. So I'm here anyway. So I was always warned, no one's going to pay attention to you if you don't handwrite. But, not too bad. Anyway, so the key point is that we're going to define somehow a set of ideal rankings. And I was talking to somebody at the break who was talking about recommendation systems, same thing. This doesn't necessarily, these can be fine anyway. You can incorporate diversity. We'll see that later. You can incorporate all kinds of things in here. There's just a set of what the right answer should be. And then it's not very complicated. We're just going to have some kind of rank similarity measure. This is the actual system ranking, and we're going to look at how similar it is to the closest one. Okay, so somewhere in here, so that's how far do we have to go to get inside the set of ideal rankings? Okay. So I'm going to talk about ideal rankings defined several different ways. We're going, and I call this, by the way, compatibility because I need a name for it. That's the only reason we call it that, because I have to call it something. So we're going to talk about compatibility with ideal rankings based on graded judgments. And we're going to look at the top 1 and top 5 from human judgments. And then we're just going to look at, I have a general undirected multigraph. How do we compute this thing? Okay, so here's an example of graded judgments. We have a set of perfect items, L4. We have a set of highly relevant items, L3, a set of relevance items, L2, a set of marginally relevant items, or whatever. And these are just a typical set of names that we have from graded judgments. And so these specify a set of ideal rankings. You notice I don't worry about the things that aren't relevant. So the set of ideal rankings are the size of L4. This is terrible math. Size of L4 factorial. So I can take all of the highly relevant things, perfect things, and permute them any way I like. And then I put all the highly relevant things next. I permute them any way I like. And I have all the relevant things and I permute them. So basically this could be for your typical offline evaluation that you might do in industry or some of the track evaluations. There are millions and millions. A set of ideal rankings is a set of a million things or more. Okay, so we do this procedure here. There's some math that I'm omitting, but in fact, if you fiddle with the persistence parameter, you basically get the same results. And I have lots of these things here. And I don't require any kind of gain mapping. So this is a kind of strange thing because I've gone from grades to something that correlates very well with NDCG if I play with things a little bit without seeming to have done anything. Okay. So there was obviously some magic happened. And the magic that happened is how I found which of the set of ideal rankings is closest. And the answer is that I take the set of perfect things and I sort it according to the actual ranking. And then I take the set of highly relevant things and sort it according to the actual ranking. Things that are not in the actual ranking just go to the bottom. I sort each set. That gives me the closest one. I can prove that you do not want the math. And then I just measure the distance with RBO. That's it. Okay. So I don't need to do this fake mapping between relevance grades and gain values. I just use the preferences directly. And I have lots of examples of this. This is just one of them. Okay. So that's the entirety of an ideal rankings from graded judgments. But I just want to make this clear that if you have graded judgments, you can do this, not a problem. You do not need human preference labels. You do not need anything. Okay. We can, however, get these things from human labels. And the idea, I said earlier, there are these problems with transitivity. There are these problems with we have quadratic numbers of items. The answer is we don't really care about most of the items. We don't really care about most of the things. What we want to do is find out what should really be at the top 5, top 1, top 3, top 10, whatever. That top with some ties as well become our set of relevance items. And so we don't need to worry about what the ideal ranking is at 100 or 200. We focus our preference judgments using some kinds of tournaments or whatever, which I'll get back to, on finding the top items. Okay. So I'm just gonna, I'm gonna talk for a while, and then we have a demo, and then we're gonna wrap up. I don't want to, I don't want to go over time or anything, and I do want to have a little bit of structure, so it's not just me talking. Okay. So I'm going to come back to how we do this. I just want to show the results. Okay. This is the first time we tried this. This is the TREC 2019 conversational assistance track data. And if we go map these, so each of these points is a run submitted to the track. Okay. So somebody said, I'm going to try to solve this task. It was a extractive question answering task. So you were given a set of passages. You had to find the passages that best answered the question. Okay. If I map it this way, this is NHC at G at 5. And you can see here are two runs I picked out. One is that starred run and one is the circled run. Okay. And if I map it this way, you can see these top runs up here actually they kind of join that cluster there. They don't stand out by themselves. Whereas if we use human preference labels, which I'll come back to how we got them, we end up with this little cluster at the top. And these are the people that successfully used query expansion methods, neural query expansion methods. And they don't actually seem to be significantly better than other runs. But once you put things side by side and say which is producing the better result, you discover that the ones doing neural query expansion do a little better, right? And that, by the way, and this was 2019. That is a traditional non-neural run. And in 2019, a traditional non-neural run on a task like this, now a traditional non-neural run would just be down here somewhere, okay? At that time, traditional run actually did kind of okay. And if you look at it, kind of like, but whereas here, that non-traditional non-neural run was there. And I know that's the best possible non-neural run that you can do because I did it. And I'm an evil old man. I know every single trick to get juice out of the BM-25 and things. And so at that time, we were still able to kind of get into the pack. But once you look at it carefully, we were just returning junk relative to the top thing there. Okay. Okay, so once again, this is just an example of what you do if you have a top 1 or top 5 in this case. And then the nice thing, come on in. Sorry, the bad thing about being in a small group is that I will pick on you. So then the last thing to do is, okay, here, I've shown you these ideal runs come from grades. These ideal outcomes are just the top 1 or top 5 or something like that. Actually, if you just have a bag of preferences, like you just derive from somewhere human preference labels, a directed multigraph of preferences. So here is a directed multigraph of preferences. It's been simplified, so it's not a multigraph, but it's still a directed graph. And so we have some preferences that say H is better than B, A is better than B, A is better than F, A is better than G. It's agnostic as to these. We have this cycle here, so we don't need to worry about transitivity, okay, and things like that. And we have this here. So this is a graph, and somehow we've asked people, or we've derived somehow we've gotten this graph, and this says which is good and which is not good. So we have some ideal rankings. Ideal ranking would have H or A at the top, okay? It would have B after H, right? It would have F after A. It would have G after A. It would have, okay. So I'll come back to that. So here's an actual ranking. Okay, we have some things that are in this graph, B, D, G, and we have some things that are not, X, Y, and Z. And so here is our closest actual ranking. You can see it's closer because A is fine is the first thing to go, and this is ranked higher here. So we have A, we have H because we have to have H next. We have B because it comes after A and it's highest here, and so on. Okay, so this now in reality I have like 7 things here or something, but in reality I would have perhaps hundreds or thousands of items. Okay, and I would have a multi-graph and things pointing all over the place. Okay, and so what I'm given is actual ranking, and I want to find the closest ideal ranking to this and compute RBO, and now I've got an answer. Okay, as this turns out to be interesting. So now a set of ideal rankings from a preference graph. Okay, how we're going to do that is there's a bunch of these algorithms. This is an NP complete problem. Like, so finding just the minimal arc set from a graph is NP hard. That's okay. basically we're going to call an ideal ranking is any sequence in the vertex that's consistent with the DAG. So it doesn't have, basically you have to omit back edges from the DAG, and then you're basically aligned after that point. And we're going to use compatibility, which we talked about here, to compute the ideal ranking that's closest to the actual ranking. And this is, of course, NP-hard. And what's interesting is we went to a bunch of different algorithms for solving this problem, okay? And what we found is a particular algorithm, which is a greedy fast algorithm from a long, long time ago. And this is probably the best way of solving these problems. So if you want to solve the problem of removing a minimal backward arc set, if you want to do that, this algorithm has been the one that's the most successful, but it has a really interesting property that other algorithms in this class doesn't have, which I'll show you in a minute. And so as an approximate algorithm, it goes fast, and it approximates this, okay? So you don't guarantee that you get a vertex sequence with minimum backward arcs, but it gets close, and there's some theory that says how close. But practically, no matter the problem that you're applying it for, this algorithm works. The really cool thing about the algorithm, and this is the entirety of the algorithm here, and I don't want to get into it too much, is that it has 2 points where you make arbitrary choices, where you decide which of the sources you're going to pick next and which of these sinks you're going to pick next. And that turned out to be, a lot of the other algorithms for doing that don't have this arbitrary choice. And so to make this work for just an arbitrary graph of preferences, what we do is here, when we pick an arbitrary sink, we pick the sink that's compatible with the actual ranking. So we want to look at the actual ranking and find a sink that's farthest down the actual ranking. And when we pick an arbitrary source, we want to look at the actual ranking and pick if we have multiple sources, pick the one that's highest in that ranking. Okay. And that turns out, exploiting that property of this this algorithm, I'm not going to show like the rewritten version of the algorithm. You can look at the paper for that. But having this arbitrary choice here lets us align our remove feedback arcs that let our actual ranking, ideal ranking, align the most with the actual ranking. Okay. And so this is preference graph compatibility is what it's called. So right now I just have a bag of arcs. Okay, I have a graph of arcs. There's no need to figure out anything about which is really the right answer or anything. I just have a bunch of preferences I got from somewhere. And so this is the top 5. So once again, this is exactly the same data we saw before. Those are those 4 awesome points there. This is just from the top 5. This is what we just saw a minute ago here at the bottom, and this is from the preference graph compatibility, and we get good alignment. And then if I go against graded judgments, we get that same effect where certain runs are popped out. Right. So 3 quick examples of if I have preferences, different kinds of preferences, what can I do with them to actually measure the quality of a search result? Yep. Yes. Yeah. These are the same 4. Okay. And in fact, so taking the arbitrary, my co-presenter here, asking clarifying questions. Thank you. That's good. These are the same 4 results. The alignment between what we saw before and this way of computing the same measure, which is a very different thing, is quite high. We've also done this on lots of other bags of preferences. I just give this as one example. Great. Okay. All right. So I just want to finish up that we are mostly talking about preference labels up till now. And preference labels are good because they're basically binary. First, we need to know we can't do preferences. We can't do a preference label between 2 things that are nothing to do with the answer. Right. If you were here, the example I gave before is like I'm looking for a vegetarian restaurant in Singapore. If I get a vegetarian restaurant in Kuala Lumpur and I get a pet groomer in Melbourne, maybe you'd say that the vegetarian restaurant in Kuala Lumpur is better, but it doesn't really matter because neither one of these are going to, I'm not planning to fly to Kuala Lumpur or take the train in order to have dinner. Okay. And I don't have a pet to groom. So we have to say, is it related? And once we know that it's related to what we're trying to do, we can ask which of these is better. The advantage of this kind of approach is that if you're doing judgments, we get much simpler relevance guidelines. I trained you all as crowdsourced assessors earlier today. That only takes one screen with no training. And we completely avoid this idea that we're going to map Likert scale into some number. It doesn't make any sense. And we're going to evaluation measures that are directly based on the preference labels themselves, and we can take preference labels from multiple sources. So this is the summary of, essentially we have, this is in 3 parts. Fernando, if you weren't here, Fernando Diaz came and did preferences between rankings. Now I've talked about preferences between items, okay, and what we can do with them, and they can come from multiple places. And then finally, I'm now going to talk about preference labels from human judgments. Does anyone have a question? We have twice as many people in the audience as I had at the beginning of the day. So I'm not sure that we should probably have done it upside down so that the introductory material comes last, right? But I didn't do that. Yes, Martin. Oh, I'm supposed to give you this.
So you spend a bit of time explaining the algorithm that you use to infer what is it, the compatibility?
Compatibility, yeah.
Right. You said it has a worst case complexity. Is it NP hard, NP complete?
It is NP hard. The actual algorithm that we're applying is close to linear.
Oh, okay. Yeah, that's was my question.
We could do like this, right? In fact, we had 2 implementations of it in Python, and one by my student and one by me. And the one by my student ran instantly. The one by me took long periods of time, but they got the same answers. So we know that she was right. So yeah, so it can write runs like in practically the computation with the DAG-based algorithm runs just as fast as Trekeval, right? Which is the important thing. Doesn't matter if it's linear or whatever, it has to run at roughly the same speed as Trekeval, right? Okay, right. So preference labels from human judgment. So up until now, I'm completely agnostic as to where the preference labels come from, but let's look at preference labels from human judgments. I'm going to talk about something that is, so basically half of what we're talking about is stuff work that we did, but I want to talk first a little bit about a paper on magnitude estimation that I don't have very good slides for, because I really wanted to talk about it. And I went to the paper and they don't actually have great figures. And so I'm going to just put up chunks of the paper and try to explain the, the algorithm. So this is the paper. This is a brilliant, I love this paper. This is one of my favorite papers on this topic. So I'll encourage you to read this paper because there's a lot of really good insights about search evaluation in this paper. And I'm going to take down this here. And I'm going to try to explain what they did. And I don't have a clip-on mic, so I have to. There are 8 of these, okay? And what you do is you show the person these in sequence. So this is not preferences. This is not direct side-by-side preferences. This is basically of that set of 8, which is the best and which is the worst. And you basically, they're presented in an arbitrary order. And then you basically say, how relevant does this seem to the search result? And they pick a number, I think between 0 and 100. And then you go on to the next one and you say, well, okay, if that was a 30, what is this? And you let them pick a new number with each one. I think you let them go back. I haven't really talked to them about this, but a sequence of 8 documents. And this is where they got a lot of the insights I talked about earlier about what the gain value should really be. Okay. And so you judge each document relevant. You can read this, or I'm just giving you the highlight. You judge each of the 8 documents relevant relative to the first one, the previous one in the sequence. Okay, and that lets you tell of that set of 8 roughly which is good and which is not. Okay, and we then use these numbers that people have given as the actual gain values. Okay, because now we're not making up some perfect, highly relevant thing. We're actually kind of putting a number on it. And so that gives you a better idea of what the gain values are. And they found good agreement with other judgments. Okay, and the real insight though came out is that you can't map a single scale into for something like NDCG. Like NDCG I showed you earlier had an exponential scale. Slightly preference is a linear scale, so there's a linear relationship between highly relevant and perfect, but there's no single mapping that works with all queries. So this was actually really good insight into the real limitations of trying to apply this very old-fashioned evaluation methodology of NDCG. So anyway, I'll just recommend the paper itself to you. If I ever do this kind of talk again, I'm going to try to get some better slides from the authors. Okay, so that's one kind of way that you could get preferences just by directly estimating them from this process. Okay, and then just apply the algorithm that I showed you from the preference graph. Okay, all right. So then we did 2 things. One is a lot of crowdsourcing of preference judgments. So here's our preference judging interface. I said we did preference judgments for check cast, and I was basically showing you how easy it is to train crowdsourced assessor for these preference judgments. We would package up 10 of these plus 3 ones that are really easy, and we'd make that a task for the assessor, and we'd pay, I don't know, $2, something like that for the task, $2.50 for the task. So lots of money earned through a lot of cash. So you are now fully trained on doing preference judgments. Here are some instructions. These instructions you can actually read, but they basically say, click on the one that answers the question better. Here's decent grammar, English grammar, and there's some additional instructions which will help you to break ties. In doing this in crowdsourcing, it is so important not to let people click equals. I burned through $1,000 discovering that we don't want people to click equal. We want to force you to make a choice, because otherwise, if you see something that looks close, you're going to pick equals. And it's actually the fine distinction that I want you to make. Okay, so how was the Never-Ending Story film received? And here we have a review of Never-Ending Story. It's a film. It's got 80% on Rotten Tomatoes, reviews from 36 critics. And then we got one over here, which just talks about it, but doesn't give any kind of reviews. So you can see it's been highlighted in green. And so that's the entirety. In some ways, we don't even need this. We just say which is better, and you pick one, and there's no other thing to do. And what we would do, we'd take 10 distinct questions and pair, so you had to read the question every time. There's a bunch of crowdsourcing best practice, and we tried to follow all that. There were some gold answers, and if you didn't get all the gold answers right, we threw your data away and didn't give you any more tasks, basically. I'm required by my university to pay you anyway, even if you give me junk, but I can still then say, okay, you're no more tasks for you. Okay. We did the same thing for Trek Deep Learning 2021, not official judgments, but we rejudged all of the highly relevant and perfect results in this way. And this is I picked this at random actually, because I just had one. So this is not quite as clear, but who is Jaffe? We have 2 ones here, and this one here is a complete biography, and this is some kind of information. And this one, in this particular example, I pulled a person like the one on the left there. Okay, and this is just one example to go along with the previous ones. So this was MS Marco data. Is anyone familiar with MS Marco data? Yeah, okay, this is MS Marco data. This is, we went and got a bunch of runs from MS Marco. This is now back 2020, 2021, 2021. Here's the ordering on the official QRLs. And basically we said, okay, on the official QRLs, let's imagine a run that is perfect. Okay. That gets the top, in MS Marco, every question just mostly has just one answer. Okay. And it's supposed to be representative of the answer. If I put that first all across the line, I would get 1. Mean reciprocal rank, 1. The one known result, perfect. However, what we did is we took all of the results returned by these runs and we had them rejudged by the crowd using that interface I just showed you. Okay, and it turns out that the perfect run then gets a mean reciprocal rank on if we take the preferred result as the best result. It could be the QRL or it could be something else. The perfect run actually gets kind of a crappy score, and we get a lot of changes in the order. And it could actually be that even at this point, what we're putting forward as a hypothesis is that, in fact, the best systems, even at this point, which is about a year or so ago, were outperforming the QRLs. In other words, the known best answers are not actually the best answers once you put them side by side and put them in front of people. Okay. So anyway, that's one of the things that we did with these preference labels. And I showed you another example earlier where we looked at Trek CAS 2019. Okay, how we are modeling crowdsourced human preferences is basically as a dueling bandits problem, because it fits really, really well. But what's interesting is that it's a little bit different. You saw well, if you were here, you saw the interleaving stuff that was done. That's also a dueling bandits problem. Here we have a couple of extra things that are kind of interesting. So we model it this way because, you know, crowdsourced preference labels are noisy, right? They're basically a person who wants to do the task as fast as possible while still passing all my gold questions. So they're not going to think about it very, very carefully. They're going to do a good job, but they're not going to do a fantastic job. So we're going to just look at human preferences through this lens. And boy, there's a lot of work done on this. So we spent a long time going through that work. If you're not familiar with the problem, basically, if you're familiar with multi-arm bandits problem, this is sort of like a multi-arm bandits problem, but not really, because basically what you're doing is pulling 2 arms and asking which one is better. So you basically specify a pair of arms and you say, you get an answer that this one is preferred or that one is preferred. And when you usually model it with some probability QIJ that says I is going to be preferred over J, but it's noisy. And when you're comparing things that are close to being equal, you get numbers that are close to 0.5. Okay. And so this has been widely used in IR and a lot of other places, but specifically in IR for a lot of online learning to rank stuff. Okay. So every time someone does a query, you interleave the search results from 2 rankers in the way that we saw earlier in the tutorial, and it gives you an answer. And from that, you try to figure out which is the best ranker. Okay. For human preferences, we observe a couple of things. First of all, preference judgments by dedicated assessors. So if you have people that are trained and are trying to do a really careful job, they're very nearly transitive. So we can assume in modeling the online stuff by as dueling bandits, we can assume a transitivity, and this is the specific transitivity that we assume, which is strong stochastic transitivity, and you can read about it there. Okay, so this is a sort of part. So this is when we started this research, we assumed we were going to look at a whole bunch of algorithms, pick one that was going to work best online, and for this particular task, and then apply that. And it turns out that's didn't work very well. So what do we need? So we can't be doing large numbers of comparisons. If we're going to do human preference judgments, we need to keep the number of preference judgments down as much as possible, because I am paying 25 US cents per judgment, and I don't want to be doing a lot of extra judgments. We want to be able to tolerate equality. And these are sort of vague criteria, but it's really important. Some of the algorithms, that are meant for dueling bandits don't really work that well if you, even practically, if you have a lot of things that are very close to equal. And we want to minimize, and this is a unique thing for human assessment. We need to minimize the number of independent assessments. We cannot go and find 200 or 300 independent assessors. We always, whatever the algorithm is, it needs to keep down to the smallest number possible, the number of independent assessors. Otherwise, the bookkeeping in a crowdsourced environment gets too complicated. Okay. And I will not go into, we were greatly aided by the fact that someone did a really nice survey. It didn't hit all the algorithms that we found, but it hit most of them. Most of the algorithms, even theoretically, do not meet the requirements, these requirements I just stated. Things what we don't want to do is we don't want to repeatedly compare to the same two arms until we find a winner. That's just increasing drastically the number of independent judgments we need. Some of the algorithms have various restrictive assumptions that we can't really map into this problem. We selected a few just to try a simulation. I threw into this an algorithm that we use for the top K judgments. So we kind of invented an algorithm that is based not on, I can explain the algorithm to anyone's interested. We tried a bunch of these algorithms. We basically first tried some very simple simulations. So we made up a case where there's one really good thing, and we made a case where there's two. So a total order with no ties and two winners with many ties to test the algorithms. Basically, a modified version of the algorithm that we had invented for a previous paper, while really there's as from a theory standpoint, it's hard to analyze, actually seems practically in this case to work. And we can point you to some literature here. But the key thing is the number of independent assessments. Like a lot of the better algorithms require, they don't necessarily find that best one very often, but more importantly, a lot of them require lots and lots of independent assessments in our simulation. Okay. So we tried this practically as well as in simulation. Okay. And once again, I call this the turkey plot, right? Because you sort of, there's kind of a bird with the arm stretched out this way. So let me explain what this is. What we did is we rejudged Trek deep learning track. Okay. So Trek deep learning track kind of partners with MS Marco. So MS Marco is huge numbers of queries with very shallow judgments, one known relevant item more or less for each question. Trek deep learning track is a subset, a small set of those questions judged very deeply. Okay, so what we did here, this is the preference graph base measures, and this is official NDCG, and this is best passage for us and best passage for them. Okay, and what this shows, this really shows that if you rejudge these things under preference judgments, the ones that do well on the official measures here seem overfit to the official judgments, to the official QRLs, right? So this here under our rejudging, one of the ones that was in the middle in the official ranking is comes out to be the best. Great. I somehow have not explained that very well, and I don't think it's worth staying around. Okay, so anyway, that is the takeaway from this. The takeaway from this is that this is the model we're using for online preference judgments. Okay, where are we? 11:08. All right. So we're finishing up a little bit faster than I thought, although we do want to get on to a demo. So we want to do preference judgments. We want to do them. We want to do preference judgments. We can do them with crowdsourcing. The model we're using for crowdsourcing is to treat them as a dueling bandits problem. So we're selecting our algorithm on the basis of that. And so that basically we're asking a question, which one wins? But what we're really trying to do is get at the underlying probabilities of one being better than the other. The other extreme is if we have fully trained authoritative assessors. So people that have been taught the full relevance criteria in the sense how do you pick them? People that are incented to do a good job as opposed to doing a fast job and things like that. So we can go in the other direction. And for that, we are developing tools that we've been using. We used it in Trek Health Misinformation this year. We've rejudged some other Trek tracks with them. And I want to end up by doing a quick demo of this, but I want to explain kind of what's a little bit different about this. So I would do the demo here, but I'm going to explain how it works before I do the demo. So we're going to see a demo of something that looks like that, except much higher resolution. Okay. Okay. So basically, we have a judging algorithm, which is meant for authoritative assessment. And as you might suspect, based on a tournament of some sort, but slightly differently. So what we want as the output is a ranking of the top K documents, where it might be 5 or 10 or 1 or whatever. And we're also going to allow equivalence classes. So for crowdsourced assessors, the lesson we learned, this costs thousands of dollars to learn it, is that if you're doing preference judgment, well, around $1,000 to learn, if you're doing preference judgments, do not let crowdsourced assessors, don't give them an equal. Don't let them say, I like them equally best. Not because that isn't true, but because if you get them, people prefer things on the left very slightly. But if you randomize it and you get them to pick something, you just get a random result, and that's fine. But what you want is the fine gradation. You want them to spend the time to figure out which one is best. Okay. In the case of trained assessors, you can tell them it's meaningful to say these are just as good. The person goes, yeah, I can't really see the difference, and that's totally fine. But it isn't them trying to sort of get through the questions really fast. Okay. So here we can have equality, and we're using basically heap, but not quite, and I'll show you why. And so it's almost like sorting or finding the top K, but it's not. And so really the lessons in what it is more of the user interface. So I don't have this animated because I didn't really trust the animation, so I took the animation out. But here is a bunch of documents that we want to judge we want to find the top K where we're going to allow ties. Okay, so the first thing we do is we put this side by side by a person, the first two things. Okay, and the person likes number 2. So we end up with a structure something like this, where we, as I say, similar to a heap, we just say that D1 is not as good as D2. So now we compare these 3 to the person still like D2. But you see what we're doing here. If we were trying to do a mechanical sorting, we'd actually put it at the back. A heap sort would keep putting them at the back. That also is another lesson that we've painfully learned. No, don't put them at the back, because the person who picked D2 here has context in their head about which is the best result. They've picked this as the best so far, and what you're showing them is an alternative. Well, do you like this one more? So their best so far is D2. Their best so far is D2 again, but now we compare D2 and D4, and we discover D4 is better than D2. So we keep this as the best seen so far. Okay. We compare again. Okay. And we discover that D4 is like, so now we just say, okay, this is the best overall. And then we take what's left of this whole structure and we rebuild it into something like this, and we keep going. And you see the best one that they saw before pops back. So this actually turns out to be, like I said, a hard-won user interface lesson that you really want to keep showing them the best thing that they've seen so far. Once they find a really good thing, you tell them, okay, that was the greatest. Now here you're going back to the same problem again. So this is, they say, well, now actually these look the same. So we build an equivalence class out of this, and we compare this. And okay, And we keep going. And so we have this as the final result. Okay, so our equivalence class shows up in here. And so now our set of ideal rankings are D4, D5, either of these two, and then the other one, D3 and D1. And as I said, when we're comparing this to an actual ranking, when we need to decide which of those two go first, we go look at the actual ranking and see which one is first in the actual ranking. Okay, and that's everything nice and linear or nearly linear, and it all works. And I think what I'm going to do is I'm going to keep going. This is worth, there's a bunch of features in this that are worth seeing. Once again, a whole bunch of, by the way, the judging tool is online. It's, it's fully nice tutorials, nice videos, everything if you want to use it for this purpose. But I'm just we'll do the demo after I'm going to actually finish we're going to finish here a little bit earlier. I'm sure nobody is going to complain, right? So we finish a bit earlier, go to the conference organizers, you say, my tutorial ended 20 minutes earlier. I want $50 back. Okay, make sure you do that, okay? So I'm just going to finish this. So this is what comes out, this kind of stuff here, and then we just apply the compatibility measures that we talked about. Okay, so I'm actually going to conclude the entirety of the tutorial except for the demo. The demo, then Nagar will run the demo, and that will be fairly short, and we'll actually have a bunch of simple questions taken from Trek Deep Learning, so we can do a short group exercise to see what we like best, okay? So I'm going to sort of finish up very quickly, though, the entire thing. So we're basically looking at preferences for offline evaluation, but Fernando spent some time talking about online evaluation, and basically there is the potential to unify the two. So we can take preference labels from human pairwise judgments, as we just saw. We can do tie-breaking things on proximity. I say I want a vegetarian restaurant in Singapore. I want the one, over in the shopping mall across the street, the Raffles Center, versus the one way in the north of the city, maybe, even if that one's a slightly better, right? In a news search, I always, even if these are articles on the same, exactly, this is the news story you're looking for, I want the update. I don't want the old news story. We can infer them from online actions. In particular, long ago, I did a bunch of work at being about skipping things, right? And if you skip something, that is a super strong signal. A click is not a very, most people here are probably familiar, a click is not a very strong relevance signal. It's a very, very weak relevance signal. Now, if it's Spotify and you click on it and listen to it for 10 minutes, well, okay, that's different. But if you're just clicking on something in web search, not a strong relevance signal. Skipping something in web search is a strong anti-relevance signal. If you skipped something and clicked on the second thing, the thing you skipped is bad. Okay, so you can infer even simple things like that. You can do more sophisticated inference, but even stuff like that, you can make these and something I've been doing a lot lately, which I will not report on at this time, is I've been asking, well, GPT 3.5, which of these is more interesting? And it likes the second one. So you actually have to work, you have to, no matter how much you mess around with the prompt, large language models like the second thing. If you say which of those two things is better, it prefers the second one, at least in my experience. Maybe your prompt is different. Maybe your settings are different, but this is what I've been discovering. So you actually have to ask twice or multiple times. Okay. And I'll end with this. So this is not about preference labels. This is about, I need a whiteboard or something. That's about this picture here. If you've never seen it, we have a set of ideal rankings over there. That set of ideal rankings does not need to just be constructed from preferences. It can take into account diversity. And in fact, here is an example from the Trek diversity component that was run, I don't know, 10 years ago or 7 or 8 years ago. Okay. And they had an official measure that took a diversity into account called expected reciprocal rank. which is a metric that in this case includes diversity. And this is compatibility, where we define our ideal rankings by basically just a very simple algorithm from it's not, yeah, here we go, from these guys here. Okay, very simple algorithm. It just says basically, if you have, roughly speaking, if you have subtopics within your query, right? And you can fix this if they're weighted differently, but the rough, simple version of the algorithm is cover one subtopic, then cover the next, and then cover the next, and cover the next. And so, and then cycle through them. That's not 100% because there's some probability weights and things that you can fix it up. But the idea is that as long as you're covering them in some order, if they're all equally important, then any of those orders are ideal. Okay. So once again, no gain. We get good, if you fiddle around with the persistence properly, we get good correlations. And we do get a few interesting things popping out. This is a algorithm by Orrin Curlin, if you know who that is. And this algorithm very explicitly tries to cluster the documents. So and in the official rankings, it's kind of, it does well, but it's kind of lost. This is the official rankings. But in our very explicit, you know, how close are you getting to an ideally diverse ranking? It stands out actually. And I think this difference is significant actually. So this whole model doesn't just fit for preferences. It also generally fits as a way of, you know, the basic idea, just say any of these things here are the right answer. It can take into account personalization. It can take into account diversity. It can take into account recency, location, anything you like. And then you just say, here is an actual result. How close did you get to one of these ideal results? Okay. All right. Thank you for your attention. Are there any questions before we do a demo and we go to lunch? One question, anything? AMA? No, but yes. Oh, good. Thank you.
It's mostly about the graphs that you show.
Oh, so I think we do theory of our model.
So the main question that I have is mostly about the graphs that you showed before about track 2021 and MS Marco. One of the things that was kind of shown that year was a kind of like a problem where the labels could only come from a subset of the data set, and what those models that had like very good MRR they identified. Do you see this kind of like the same behavior when you do preference? Like when you do the preference, could you have some kind of problems of searching for a subset of answers or being limited to some models?
So the very poorly explained plots that looked like a bird sideways like that, those actually kind of were related to that point of what the models were trained on, right? So in fact, the points that did well in many ways, if I had explained it properly, right? If you had basically trained on MS Marco, right, you would do well on deep learning, okay? But under the preference judgments, you would not. So that the fact that the QRLs were drawn essentially from the same source, you know, was actually significant. And I think it's related to the observation that the relevant stuff was pulled from a sub collection that was like the MS Marco, right? And so I think the actual systems had been overfit to the MS Marco collections, right? But I have to, you know, Nick Creswell, right? If you know Nick Creswell violently objects to these conclusions. So I just have to say that we wrote a paper that will actually be presented again at ECIR if you're going to ECIR, in which some of those plots were taken, and we concluded that in fact the methodology had reached its limit. Not that it had been bad before, but basically now that we concluded that we started with the hypothesis that the system, which other people had noticed, that the systems we're basically surfacing documents that seem to be better than the actual QRELs, right? And we found support from that. And Nick does not like our conclusion. So I will throw in that when I say this is true, Nick will tell you, no, subsample. He has another argument that says why we're wrong. And that's cool because science, right? Okay. So we're going to do a demo and we have that set up, right? And I'm going to turn it over to Nagar, who actually did a fair amount of this work that
Okay. Hi, everyone. My name is Negar. I'm a PhD student at University of Waterloo. Charlie is my supervisor, and also I did an internship with Fernando, who spoke earlier. That's how I know this guy. So I'm going to show you a tool which is called JudgeGo, and is designed for preference judgments in the authoritative assessment mode, which means that the assessors have been trained. It's not like crowdsourced. And yeah, okay. So if I go back to the slide, this is the demo is working based on this algorithm that Charlie explained earlier. So I'm going to log into the to this tool and show you how it actually works. Okay, so when you log this interface has two modes, one for admins who wants to run assessments and one where you can log in as an assessor. So now I logged in as an assessor and I want to show you how we can judge using this. And this tool is up online. You can use it to run your preference judgment. It has been used for health misinformation check for 2022 to collect the relevance judgments for that. When you log in as an assessor, you see several topics. Now, as an admin, I have been assigned some of these topics to myself, to this user as an assessor. So you can choose which topic you want to answer. I hope you can read the topics, right? So let's say I want to see I want to judge documents for the topic, can coffee help you lose weight? The answer is yes. I go start judgment, and this is, I think I'm more comfortable like this. Okay, so this is the page that you see. What? No, I'm comfortable. It's okay. Yeah. Okay. Okay. So you see two documents. This is basically how you are going to see which one you prefer. The documents has URL links. You can click on them, see if it's, yeah. So these are the documents, and you can click in to see actual documents. Also, you can see the parsed HTML thing and the content. So it has some cool features to help assessors to assess more efficiently. First of all, it has a search bar that you can search for some keywords. So let's say I search for coffee, and then the terms that you search will be highlighted in a specific color. I will search for weight. It comes in another color, so it helps assessors to focus more on specific parts. And another option that it has is that you can highlight some parts, and the highlighted part will remain. So because you're going to see this document again and again in future, so the highlighted part will remain so that you can focus on the more important parts. So the topic has also some description. If you look, click on the topic information, you can see more. So in terms of trade topics, sometimes topics has like a description. It tells you more if you don't know about that. You see the estimated number of judgments to finish the round. If you seen when Charlie was explaining, the algorithm has several rounds, and you see how many judgments you need to make before the round is finished. So let's say here we decide that the one on the left is more relevant. So I'll choose here you can choose if you prefer left one, right one, or equal. We have the equal options here because it's not the crowdsourcing assessment. Okay, so the one that I selected before, this is the one that I highlighted, right? It will remain on the left. And this is, here we see this new label. This is a new document. So it means when the new label comes here, it means that the assessor has not seen this document before. So the good thing is the assessor needs to read and go through only one document at a time because we already read this. So I can also, like, I don't know, I can search for lose weight. And let's say, again, I prefer the one on the left. I want to finish one round to show you how the results will come up. Again, this is a new document. Let's say this time I don't know, I go with the right one. This one doesn't seem like it has so many of the terms that I searched for. I'll go with left. Let's say this one, we say equal. Okay, so now one round of the judgment is done. And as you can see, we have different level of grades. And this between the three documents that we've been judging, one of them has been assigned in grade 1 and 2 of them in grade 2. It's like this one that Charlie was explaining. It's like exactly this is how it will show up in the demo. And if you want to, yeah. And so you can continue with next round of the judgment. So this time we only have 2 judgment remains because we are in the second round. Another thing is that if you go to the home page, you can go to the profile of the assessor and see how many tasks it has been assigned to, a number of judgments that they need to make. Yeah, and this is pretty much it about the assessor's page. And also there is admin side of the tool, the JudgeGo tool, which you can basically, it's like you can assign tasks like topics and a set of pool of documents for each topics or queries and assign it to different assessors. If I go to tasks, the previous user that I was showing you was like test demo, and these are the topics that has been assigned to the user test demo. And this is the documents that we judged together, like can coffee help you lose weight? And it says number of answers that it has been collected. Yeah, and that's it. If you want to try the tool, it has a GitHub. And it has a GitHub page, and I can show you, it has a Docker. You can run it on your local network, or also you can use the website if you want. Yeah. Yeah. Yeah, it was health misinformation. Yeah.
So there's a lot of hard-won lessons in that interface. I would love if somebody's trying to do an evaluation test and wants to use a tool like that. By the way, you saw the URL. If you want to go there and play with it, let us know so we can set a few tasks up for you. Don't just hack the site, please. We've done this on a few things. A lot of hard-won lessons behind this. I mean, it looks like what you'd expect, but at the same time. So if you actually want to try a task like this in an evaluation exercise, we would like to support you. There's actually a site, right? There's a GitHub site that actually has a full tutorial and all of the code. and videos for how to use it and stuff that we want to try to keep developing. All right, that is, okay, so, if you go complain to wisdom organizers, you say, we only got 2 hours and, yeah, 35 minutes of tutorial, but sorry. I was supposed to be speaking into this. We're almost done.
Well, first of all, thank you both and Fernando for the tutorial. But since we still have a bit of time, and since I guess quite a few of the people in the audience are early stage researchers, could you reflect a little bit on some of the limitations and the sort of open issues that you think are worth running after?
That's great to go back to this. So I'll start with the open issues, and I think this is the one that interests me the most. I would love to have somebody who has. I wish I could go back in time to when I had access to a lot of online data, and I would love to be able to see if we can merge offline with online assessment. For that, you need your own search engine, commercial search engine, but people have that sort of stuff. So the limitations of this is that it's like the limitations of every single new thing that's ever done, which is that we have 40 years of doing academic evaluation exercises. And we have 20 years of doing commercial evaluation exercises that are largely based on point-wise assessments of individual items. We have a few people, Ben Carteret, 10 years ago, put maybe 6, 7 papers out on preference judgments. Lately, we've put out about a single number of papers on preference judgments. People have done similar efforts, 1 or 2 papers over the years, but the amount that we know about how to make preference judgments work for evaluation relative to how much we know about graded assessment is relatively small. So if you want to use this in practice, I would love to talk to you to see if we can figure out the things that we learned and translate to you. And the last thing I want to do is, and this is something where I just spent a lot of time. I can't go into details because we have something in submission, but spent a lot of time trying to understand how we can fit, like everything else, how we can fit large language models into this kind of thing. Because in fact, large language models are pretty good at relevance judgments. They're not as good as humans, as far as I can see, but they are pretty good. And so I think the big research question is search and recommendation, are they done now? Because we just ask ChatGPT, which is the best thing? I don't know. And if we are still using, if we still need to make progress, how do we figure out what that progress is? And I think fundamentally, we cannot make progress without tying it to people. So, but at the same time, maybe we can reduce the level of people by using large language models to do a certain amount of assessment. So that was a very long, complicated answer that said 3 things, right? One is that I think there's a lot of work to be done here, especially specifically in figuring out how to merge online and offline, but also just trying to figure out, okay, we have 40, either 20 or 40, depending on what years of experience doing individual graded assessments. There's still a lot of filling in the blanks and saying this doesn't work and that doesn't work. That's one thing I said. And the third, and basically the last thing is we're living in a new world now. So how do we transfer the best practices of the old world into the new world? We've reached a point where, yeah, as I said, if you just ask for relevance assessments from large language models, they do a pretty okay job, right? Not as good as humans, but pretty okay. And that could change. And as a classification test, they're actually not going to hallucinate the answer or something. You say this, that, turn the temperature down, they give you an answer. Is that enough pontification, Martin? Oh, sure, sure. So yeah, you want to come up? We can do a mini panel or something if you want to.
I'll just ask questions as well. So one thing that has always intrigued me with human judgments is that they're not stable. People learn stuff, people change their mind, they find out facts about life, etc. And so we know a fair bit about non-stationarity for pointwise judgments. Do you have any insights to share about non-stationarity in this preference-based setting?
I have two things to say. One, we didn't demo the undo button. So that's a very specific answer to your question, that one of the harder lessons is that people want to be able to say, oh, wait, I've seen now 6 things. Okay, I want to go back and I want to start over. So you can actually, in a very narrow and specific way, one of the hard lessons we learned is to be able to let authoritative assessors undo their answers. And the other answer is that I think that's one of the open things. I've done one test where we did authoritative assessors against crowdsourced judgment, and we got pretty agreement is sort of funny because you can't apply it's not a classification test. You can't apply like Cohen's kappa or something, because in fact, there's a whole bunch of stuff that's kind of meh. And if you sort of did a lot of crowdsource and tried to estimate them as a dueling bet, you discover the probabilities goes to 50%. People aren't sure because they're both kind of meh. So what we do is we compare different methods. Do they produce the same top results, right? And we had one direct comparison between highly motivated authoritative assessors and crowdsource, and they produced basically consistent answers. So the very high tau correlation, I think maybe 40% of the time, the top result was the same, but then there's another 20 or 30%. And I'm just kind of pulling these numbers out broadly to where the best result from the authoritative assessor and the best result from the crowd were completely different. They're not even in the top 5, right? So, there's still a lot of work to do on that kind of stuff, right? And what is the right way to approach these kinds of things? This is exactly part of what I was saying about we've got 40 years of one, and we've got a few determined efforts and some important papers on the other methods. So we're still figuring this out. Yeah. So Martin and I have been bantering at each other. I can take another question and then I can give you back 19 minutes. Anyone? Yeah, I'll just bring this down to you and I'll stand next to you so that I don't have to run back.
Thanks. Thanks for the tutorial. So you mentioned that the users or the crowdsourcers are a bit biased towards the left answer. So I wanted to know if you have seen other types of biases, like if they prefer the shorter answers or answers with numbers, maybe.
So that's a very good question. No, and in fact, we tell them that if you think that actually short is good, so I wouldn't call that a bias. I mean, one of the important things is we randomize every step of the way. We randomize the order of these things because I think people tend to just pull a little bit to the left. Like if they're equal, they'll go a little bit to the left. So we want to kind of take that out, but otherwise and large language models, if you give them preference tasks, at least the ones I've given them, they like the second one a lot, actually. Like I'm not sure what it is. I didn't want to spend I have a whole extra hour talking about the things I've been doing with, GPT 3.5 on this stuff. And it's all very interesting. And one of it is, in fact, that as far as I can see, seems really, really consistent. No matter how you prompt it, it goes likes the second one more. That, kind of almost makes sense. Like I don't ever try to have a mental model of how GPT 3.5 actually works, but it is interesting how consistently it likes the second result, right? It's sort of like 60 to 30 or something. So that means if it likes the first one, that is really the right answer. Okay. But yeah, there's lots of stuff to do. So I have one more quick question. Okay. Yeah, no worries. We got time.
Yeah, if you do some kind of graded preference assessment, like you say, it's much better, slightly better, etc. Does it improve the granularity of the evaluation?
So I have not tried that. I think the magnitude, like the magnitude estimation paper that I presented very poorly because I couldn't find any good figures out of their paper that I could just put up. I think suggests that, that's things that people can do. They can look at something and say that's about a 10, and they look at the next one and go, oh, that's a 40. And they look at the next one and go, okay, that's a 30. And so that I think the magnitudes there, that paper shows those magnitudes actually have meaning, like they actually do relate to back to grades and things like that. So I think these are like, there's this, in this talk, we really tried to separate out preferences between rankings, which mean one thing, preferences between items, sort of agnostically in terms of how you're eliciting them, and then how you actually specifically in one case, couple of cases, elicit them. So I saw there's a lot of work in the last part. If you're actually going to try to get these out of humans, what's the right way to do it? And there's also a lot of work to do in what do you do once you have them. Okay.
Thank you for the presentation. Throughout the presentation, you were always speaking about neural rankers. But my question is what about non-neural rankers, like classic rankers? Are they already outdated, or they're still like researched? For example, the gradient boosting.
So this is 2023. So I can't get up here and not say neural ranker's good, right? I do think, like gradient boosted decision trees work really well in rankers, right? So I can't say that isn't true. I'm just saying especially from an academic standpoint, over the last 4 years, we've gone from, I showed you, look, there was a Trek task, right? And with some, like I think we submitted a neural run as well. But I, as a devious, evil, experienced old man, sat down with tools that I have and actually nobody else has, and produced a non-neural result that could live with the best of the neural results on traditional evaluation. I can't do that. Okay. And when you look at these results, they are producing things where everything looks good. Right. So now I think you could have done this before, but it didn't feel like there's a need for it. Right. But now if we're going to make any more, we've reached the point with, neural methods that if we're going to actually be able to say, look, that's better than this, we are going to need some finer instruments, that can more precisely say, yes, this is better than this. But any of this could apply. We could have done this 20 years ago, not a problem. Right? If that was the question. There's nothing special to this having to do with neural rankers. It's just that suddenly everything is so good that we need to, this is my real motivation for doing this was that thing with Trump. That was literally my job, was to come up with a valuation that didn't make those equal, right? And at that point, there was very little. We were just touching neural ranking, right? So that was 2017, 2018, that kind of range, right? Okay. Right. Okay. It's lunchtime. Oh no. I'm still fine. I'm happy to stand here all day. I feel like people are going, oh, when is this guy gonna stop?
Yeah, first, thanks for the fantastic tutorial. Yeah, so you have mentioned that we have been using this pointwise judgment paradigm for like 40 years. And I guess one of the reasons is like this paradigm is, well, very good for ranking optimization algorithm because it's very easy for us to develop some ranking functions or ranking models to directly optimize this type of, the pointwise judgment stuff. So I'm wondering, what do you think are the challenges or opportunities when we move from this pointwise judgments to the preference judgment, or are there any difference?
Learning to rank systems have usually been trained with either listwise or pairwise type things, right? And they're applied pointwise, but they're trained they've for a long time been trained pairwise or listwise, right? So this kind of just fits in with it. But at the same time, I have not tried to use this as training data. Okay. I think that is something, okay, collect this stuff, use it as training data. But actually preference labels are becoming more and more important. I mean, the reinforcement learning with human feedback type stuff, those tend to be preference labels. Here are two things that were generated, which is the best one. So I think, from that standpoint, yeah, there's work to do, but this is sort of always how we've been doing this stuff. That's just how we've been training rankers, is with pairwise labels. Now, something like Lambda Mart has built into it NDCG, but that was kind of like the hard work was cranking NDCG, which is, into the loss functions, right? How do you do that, right? And so I don't know. And we can talk about that later, but I'm not talking about training data, but you could use this to build training data. And I think that's the direction. Also, if for a long time, most learned rankers were applied pointwise. Now there's a lot more rankers that are applied, like the actual application is to give you two things and say which is better. Duo T5 and those kinds of rankers, right? Okay.